Hello, young chemists. What is up? It's Mr. Rosen. Today we're going to talk about the combined gas law, which is our third gas law we've learned. And the combined gas law, kind of as the name implies, is a combination of two other gas laws. And those other gas laws are Charles' law and Boyle's law. So Charles' law was looking at temperature and volume. We had a video on that. And if I take the combined gas law, which is written here, if I cover up P1 and I cover up P2, okay, what I'm left with is, I'll just try to cover it this way, what I'm left with is V1 over T1 equals V2 over T2. That's starting volume over starting temperature equals ending volume over ending temperature. That's Charles' law right there. Now, if I let go of it and I now cover up the temperature, right, temperature 1 and temperature 2, what I'm left with is P1 V1 equals P2 V2. That's Boyle's law. Shows the relationship between pressure of a gas and the volume of a gas. So the combined gas law, as the name implies, is a combination of both of those equations in one. Now, this is how the combined gas law is usually written, but if you take this and rearrange it, you can get this equation here on the right. I encourage my students to set up their calculations this way. If you do that, then solving becomes as easy as just doing a single division step. So it's just a one-step division problem when you set it up this way. Right now, it's common for students to go, P1, V1, T1, P2, V2, T2, but you need to know the temperatures are switched. Okay. Also, a note on temperatures, make sure you're in Kelvin. Always make sure you're in Kelvin. So we're going to do a couple of example problems. The first one says, Mr. Rosen fills a balloon with 6.5 liters of helium gas in his classroom, which is at 1 atmosphere of pressure and 295 Kelvin. So this is kind of, on a normal day at sea level here, our atmospheric pressure is going to be very close to the pressure of 1 atmosphere, 1 atm. And this is pretty close to the temperature of the classroom, 22 degrees Celsius. So I fill a balloon with some helium in my classroom, and it has a volume of 6.5 liters. It says, Mr. Rosen releases the balloon and watches it float away. If the balloon rises to an altitude where the temperature is 258 Kelvin, okay, so the temperature is decreasing, and the pressure is 0.725 atmospheres, what will be the new volume of the balloon? So in this question, we have a starting temperature, pressure, and volume. I let go of the balloon and it floats up higher in the atmosphere. And higher in the atmosphere, the atmospheric pressure is lower. So the atmospheric pressure lowers and it gets colder, so the temperature goes down. So what's the new volume? Now, before you even start, it's good to think about, maybe predicting the way it's going to change. And based on the temperature change, right, temperature is decreasing. So if temperature decreases, you would expect the volume to decrease. But at the same time, the pressure is decreasing. And if pressure decreases, volume increases. So one is going up, one is going down, right? Based on the change in pressure, the volume should increase. But based on the change in temperature, the volume should decrease. So we actually have to do the math and figure out which of those two is going to be the greater influence on the overall change in volume. So the first thing we're going to do is identify each variable. What do we know? What are we trying to find? So the volume that we're starting with is 6.5 liters. So 6.5 liters. The temperature is 295 Kelvin, and the pressure is 1 atm. the balloon rises and the new temperature is 258 Kelvin. That's a 5. 258 Kelvin. And the new pressure is 0.725 atm. What will be the new volume? So that's the unknown. We don't know what the new volume will be. So we're going to now plug this into the equation, which again is P1 V1 T2 equals P2 V2 T1. So 1.00 atm, that's our starting pressure. Starting volume is 6.5 liters, and our ending temperature is 258 Kelvin. Our ending pressure is 0.725 atm. Our ending volume is unknown, and our starting temperature is 295 Kelvin. Now notice our temperatures are in Kelvin, that's important, and notice that I have P1, V1, T2, P2, V2, T1. Now I'm solving for V2, that's what I'm solving for. If you're going to solve for V2, this is our variable, right? This is like X. You need to get V2 all by itself on one side of the equal sign. So to do that, I'm going to divide by the other stuff on that side. So I'm going to divide by 0.725 atm times 295, that's a 9, Kelvin. If I do this, atmospheres here will cancel, Kelvin will cancel, and what we'll be left with is just V2 on the right side of the equal sign. Right? And that's what step 3 here says. Isolate the desired variable by dividing both sides of the equation by the two variables given on the side of the unknown. So this is the side of the unknown. We're going to divide by the two things on that side. But whatever we do to one side, we're going to do to the other. So this over here is going to get divided by 0.725 atm times 295 Kelvin. So this is basically P1 V1 T2 divided by P1 T1. Or sorry, P2 T1. So we're going to multiply the top three numbers. I'll bring my calculator in here. I'll do it on this side. So 1 times 6.5 times 258 gives us some number. Okay, now it's going to get divided by, now you have to be careful with order of operations. Sometimes students say divided by, and they just punch in 0.725, and then they hit times 295, and that will take your answer and divide it by this number, and then whatever that is multiplied by this. But you actually want your answer divided by the product of these two numbers. So open parentheses, 0.725 times 295, close parentheses. So now that this is in parentheses, the number on top is going to get divided by whatever these numbers multiplied is. And that gives us 7.84. Okay, now that's the number, but it's a volume. And if you look at our units, atmospheres divided by atmospheres cancels. Kelvin divided by Kelvin cancels. And the only unit we're left with here is liters, which is a unit of volume, which means our V2 is in liters. Now, if we look at how things change, our starting volume was 6.5 and our ending volume is 7.8. So the temperature actually decreased, but the overall volume got bigger. So if the temperature decreases, you'd expect the volume to decrease, but it actually ended up increasing. And so what that tells you is the change in pressure has a greater influence overall than the change in temperature, right? So even though the temperature decreases, there's still a net increase in volume. We're going to do a couple more examples. We'll pick up the pace a little bit on these. So question number 1, says a sample of carbon dioxide has a volume of 25.5 liters and has a pressure of 3.2 atmospheres at 303 K. So I always just like to start by listing what we know and what we're trying to find. So we have P1, V1, T1, and then we'll say P2, V2, T2. What do we know? What are we solving for? So this tells us the starting volume, temperature, and pressure. Starting pressure is 3.2 atm. Temperature is 303 Kelvin. And volume is 25.5 liters. If the gas is compressed to a volume of, okay, so it's getting squeezed into a smaller volume, so the new volume is only 18.1 liters, and the temperature is being raised to 458 Kelvin. They're saying, what will the new pressure be? So we're solving for P2. Based on our changes, you can see as volume decreases, pressure increases. So if our volume's decreasing, we'd expect our pressure to increase. And the temperature is also increasing. As temperature increases, pressure increases. So both of our variables are telling us that pressure is going to increase. So we should absolutely get a number for pressure that's more than 3.2. But let's plug them into the equation and see what we get. Okay, so 3.2 atm, that's P1, times V1, 25.5 liters, times T2, which is 458 Kelvin, equals P2, which you don't know, V2, 18.1 liters, and T1, which is 303 Kelvin. So again, the most common mistakes are not converting to Kelvin or putting temperatures in the wrong place. We're solving for P2. That's what we're trying to find. So we need to get P2 all by itself on one side of the equal sign. So I'm going to divide by 18.1 liters times 303 Kelvin. That will cancel these out and leave us with just P2 on the right side of the arrow. Whatever we do to one side, we're going to do to the other side. So this side gets divided by 18.1 liters times 303 Kelvin. Bring my calculator in here. So 3.2 times 25.5 times 458. That's a big number. Okay, now it's going to get divided by, remember, order of operations, open parentheses, 18.1 times 303. Sorry about the bell. Close parentheses, that equals 6.81. Now, 6.81, again, let's check our units here. Atmospheres, okay, well, here's liters and liters, so liters are going to cancel. K and K is going to cancel. Our only unit left is pressure, which is ATM. So 6.8 ATM, our pressure did increase. Okay, in fact, it more than doubled. So that makes sense. All right. The last question, same sort of setup here, P1, V1, T1, P2, V2, T2. It says, a sample of neon gas has an ending volume of, okay, so it's important to read the problem because just because this number is listed early doesn't mean it's the first volume, it's the ending volume. So this is 5.4 liters and ending pressure of 1.25 atm and the ending temperature was 298 Kelvin. If the starting pressure was 5.78 atm at 885 Kelvin, what was the starting volume of the gas? So this is what we don't know, V1. That's our starting volume of the gas. Okay. So we're going to solve for V1, which is on the other side of the equation. But we'll set it up like normal. P1, 5.78 ATM times V1, so we don't know, times T2, which is 298 Kelvin, equals P2, so 1.25 ATM, V2, which is 5.40 liters, and T1, 885 Kelvin. Now this time the variable we're trying to solve for is on this side, which is a little new to us. But the math is the same. We need to get V1 all by itself on one side of the equal sign, so I'm going to divide by the other stuff that's on that side, 5.78 ATM, times 298 Kelvin. That will cancel these out and leave us with just V1 on the left side. But whatever we do to one side, we're going to do to the other, so this side gets divided by 5.78 ATM times 298 Kelvin. Now, atmospheres divided by atmospheres will cancel. Kelvin divided by Kelvin will cancel, and it will leave us with our volume in liters. Okay, so let's plug these numbers in. 1.25 times 5.4 times 885. Okay, again we get almost 6,000. That is going to get divided by, open parentheses, 5.78 times 298, close parentheses. See how that number's in parentheses, it's very important. Otherwise your order of operations will be wrong. Hit enter, and my answer here is 3.47 liters. That is my starting volume. Okay. Now, just kind of look at our answer. We can think about things here. The pressure decreases. So based on the pressure decreasing, we would expect that the volume would go from something to larger than where we started. Okay. But at the same time, the temperature is decreasing. So based on the temperature change, we'd expect the volume to be smaller afterwards than we started. Now, overall, the volume gets bigger from where we started, which means that the change in pressure has a greater influence on the overall volume than the temperature change does.